Hi, in this video we'll go through a question set on my note which is about data analysis, and you also get to apply what you learned from linearization in the previous video. For the data that I provide to you, it is actually from a real experiment, and if you want to get this data digitally and with an Excel file, I'll put a link in the description below. You can download that. So make sure you have done and try your best to complete these 2 pages of question before I show you the answer. It will be very helpful if you do so. So pause the video now if you haven't finished.
2,000 years later.
Alright, so the first part of the question I asked you to do is to create the process data table. And after that, this process data table should be enough for you to produce a linearized graph. So according to what you learned in the previous video and also the background information here, there is an equation telling you the relationship according to the theoretical framework between s distance and h with whatever height it is. I don't want to provide you with the content because that is not relevant to our work. We can just work with this equation, and I don't want that IA topic to get exposed to you simply. Alright, so just stick with this equation as the theoretical framework, and then you can already tell, according to what you learned in the previous video, that s proportional to root h, and that's why in your process data you would want to include root h, because later on if you try to plot s against h, that's gonna be a curve obviously because of this established relationship, and therefore instead of plotting s against h, we should be plotting s against root h, and in this case you should find a straight line hopefully, and the slope you can also tell it should be what? It should be 2 root x. X is some sort of control variable. Of course, I simplified the equation. The original equation is slightly longer and a little bit more complicated, but doesn't matter. This is just a practice for you. So this is the file that you will see if you download with the link that I provide to you. So let's plan ahead here. So what do we need to add in the new column? One thing that we should do obviously is the average distance. Okay, that's one thing. You may need to calculate, you should calculate the new uncertainty of all these. Because of the trials, they have fluctuation, so you have to use a half range method to find it. And number 3 is to find out, like we said, the root h for making the graph linearized. So give me some time, I'll work out the heading first and I'll get back to you.
A few moments later.
Okay, so these are the 4 column heads for the process data table that you need. Again, that should include square root of the height and absolute uncertainty of it. I forgot to mention the average distance and also the absolute uncertainty for that. So let's just work out the formula one by one. So for square root, it should be quite easy. You can search on Google to find out how to calculate in Excel the square root, or you can just try your luck. SQRT actually is, you can see, square root of a number. So double click that and you have to follow the syntax. Is SQRT bracket the number, so this is the number you're looking for. And again, control and paste. You want to keep it as a good decimal place or significant figure. Here will be SF because you are doing multiplication basically. So I would keep it as 3 or 4, it depends. These are 4 and these are 3, so I can keep this as 4, okay, and then these will be 3, so like this, okay. As for the absolute uncertainty, then we have to think about the formula first. Alright, I assume if you are doing in your IA, you have present this in your report as well. So we want to find out root h uncertainty, then that will be root h average, and since we should know h delta over h log, but then now with a square root actually means to the power of 1 over 2, so that's why according to the law that we learned, this is the calculation that we need. And therefore for the value of the uncertainty itself, absolute uncertainty itself, then it will be this thing multiplied with the root h log. So that means in our case, for example, this one, that should equal to 0.5 first, right? Multiply delta h. Delta h is 0.05 according to whatever is done previously. Actually, that should depend on the precision of your instrument. Anyway, so next is divide h log. So divide this, all right, this is h log basically, times the root h log. So that is basically what you did just now. Okay, so these are the absolute uncertainty. Okay, and again, normally we would only express it with one sig fig. So here you go. Okay, and whether or not they match with the average, right, is something we have to look into. So these are fine because these are all up to 3 dp, right, for these pairs of data. So they are fine, but then for these it's not, right? So that's why you need to round up the uncertainty to match with the decimal point that you have for the average value. So that would be 0.0. Actually, can I actually do this? Oh, actually you can. You can actually. I mean, the software will automatically round it up to you. So very nice. Next, the average distance. So according to what we talked about in chapter 1, then for average, normally in mathematics you take the mean, so add them up, divide by 3. Then we actually would use the maximum plus the minimum divided by 2. So what you can do is you can do the maximum among this range. Okay, if you just try to check that, yeah, this is 5.5. So if you try to continue to edit it, then like we said, we want to minus the minimum. Actually not minus, plus, right? Because we want to find average. Minimum. All right, double click it and select the range again. So then typo. No, there's no typo. Are there any typo? Oh, I think the close bracket, they will automatically do it for you. So let's not forget to divide by 2. So you can also add it here, divide by 2. But then since they will do the division first, so you need to add another bracket here. Okay, so 5.1. So you may want to double check manually whether or not it is true. I mean, in our case, 4.7 and 5.5 add together will be 10.0. 10.2 divided by 2, then yeah, 5.1 is correct. So in that case, I guess you can be confident to use this formula for the rest. So copy and paste and done. And again, you want to keep this as 2 sig fig only. Oops. 2 sig fig. Okay, here we go. And that's it for average distance. For absolute uncertainty, we'll be again using the half range method, and the formula is very similar. So we would have to do same as the one for this, but then we'll do minus. So let me do it. Maximum, double click, select the range, close bracket, minus the minimum, double click, select the range, all right, and add a bracket to it, divide by 2. Okay, so here you go. And again, we want to keep this as 1 sig fig only. And that's all. So this table is the process data table that we need to include in your IA. So you can include it here for your reference and for your revision in the future as well. So assuming we have this table, then we will be able to plot the graph and also the error bar, and you'll be able to add the max min line. So I will not be demonstrating here. You can always find again many other videos on YouTube, and you can try it out, because for different software the buttons are at different positions. So for Looker Pro you can do it, for Excel you can do it, for Google Spreadsheet you can also do it. But the idea is the same in general in physics, but it's just the buttons are different. So I think you can just go online and find out how we can do it. However, one thing that I would like to do is just simply by using our own data, and you can try that as well, and to just plot them into the graph and see whether or not that is really generating the graph that I show you later on. So here we go. So this is the graph. It is kind of a straight line, so I think the data are pretty nice, and yeah, that is basically the same as the one that I provide to you in the question below. So I think that's why you can then construct a straight line, and then you could, yeah, of course, when you construct a straight line, by the way, that's one thing you may want to pay attention. You don't want just to get the line from the first data to the last data. Instead, you should draw a line that is going through the x and y axis. So a line here and a line here. So there's a certain way you can do it with your software. So again, I'll pass that responsibility to you. You can find out on Google and YouTube. Back to the question. Question 2 asks you to label x and y axis. So obviously, x axis is root h. You can put down the name if you like to, and then the unit is root cm, or you can put it as cm to the power of 1 over 2. It's the same. And for the y axis, it's gonna be s average. Okay, and the unit would be cm. Yeah, that's it. And notice one thing is that even though we have processed the data, we should still keep the one that is supposed to be the independent variable on the x-axis and the dependent variable on the y-axis. Question number 3. So let's say from the software you already find the equations for all 3 lines. So what you can do is you can see there are 3 different slopes for these 3 lines, obviously, and so you have to express it. So what you can say about it is the slope will be firstly bounded by 2.10 and 1.73. So that is to say the slope would equal to, again using the way that we take average, maximum plus the minimum divided by 2, so you get 1.915. So let's write it to 1.92 plus or minus the maximum minus the minimum divided by 2. So you get 0.185, and then you round it up to 0.19. Okay, so here, since we have the uncertainty to be 1 something, so if you remember what I said in the earlier videos, then you could just keep it like this. That's one way of doing it. The other way of doing it is you could, if you really want to, you can further reduce it to 0.2. And in this case, then your average value also got to change to be 1.9 only, right? Because they have to match the decimal point. Okay, so both of these should be accepted in the Physics IA. However, you should put down the units as well, alright? But then I think for that, we can answer that after we find out 3B's answer. So 3B is asking you the meaning of the slope. So once again, go back to the equation. Okay, let me erase this, and let's just try to think about it again. Since what we do now is to find out the slope, and again in the graph of s against root h, the slope would simply be s over root h, right? Physical meaning of this. And so that, of course, there will be delta here, right? But then let's just ignore it. And then if you rearrange this formula, then we should get 2 root x. Yeah, so that means this is the meaning of the slope. So you can say slope will actually means 2 root x. And of course, x is something that I kind of hide here in the actual context, that you can refer to whatever the physical meaning of it. So if you really want to work out the unit for the slope, then you could actually deduce it from here. So that's actually is cm divide cm root. So actually should be root cm as well. So that should be at here. because it was cm divide cm root. So yeah, cm root will be the unit. Okay, so I insert, okay, I'll just do it here, cm root. Okay, so this will be the units that you should express also for the slope. Next part, question 3c. So it asks you about the y-intercept and its uncertainty, because this is also something you want to look into when you analyze the graph. So other than the slope, very likely your y-intercept will also be meaningful. So other than by looking this from the graph, which you may need to extend the line and then you can look at the marking, but then since you already get the mathematical equation here, then you don't have to do that actually, because the y-intercept is already here. All right, it's negative 2 point something, 3 point something, and 1 point something. So what you can do is again do the same thing. So you can say y-intercept will be once again the maximum, which is 3.09, or you can call it the minimum. It doesn't really matter because all of these are negative anyway. So plus 1.84 divided by 2, so you get 2.46, but I guess you should get only up to 2 dp, so 47. Same for the uncertainty, which is minus the max and mean. So 3.09 minus 1.84 divided by 2, you should get something like 0.625, and then you round up to 6.3. Okay, and this time, because this digit is not 1, so we must run it up to 1 sig fig only. So that is to say this will be 0.6, and that means this one will be 2.5. Okay, so this will be the y-intercept, and for y-intercept, that should be in the unit of cm in this case. Okay, so bracket cm. Oops, I missed out the negative, so actually it's negative 2.47 plus or minus this one. This one doesn't matter if it is negative because you have plus or minus anyway. And then this one is negative 2.5 plus or minus 0.6. Alright, lastly, for question 4, is asking you whether or not the result will have significant random error and significant systematic error. So if you haven't done this part yet, please pause the video, really try to think first, and then we'll talk about the answers.
A few moments later.
So for random errors, there are actually 3 ways available for judging it. So number 1, very simple, just by seeing whether or not all 3 lines, max mean line and also the average or the line of best fit, will pass through all the error bars. So if you try to look at that, I think yes, yeah, I think this is good. I mean, at least from our graph here, it is good. There are times, again, you may have a data just somehow, maybe, let's say this one, move a little bit more down, or more like this, right? Then there's no way you can draw all 3 lines that pass through it, right? Literally no way. So in that case, there would be a random error happening at that particular data point. So the first approach is saying, I mean, let's put down by checking the max mean line and also the line of best fit, all error bars are covered. So the answer is no, no significant random error. The other way of doing it is it depends whether you want to actually find out the physical meaning of the slope. So if you want to do that, then one way of evaluating the random errors could be try to find out the percentage uncertainty of the slope. So in this case, that's gonna be 0. Well, let me just take the blue one, 0.2 over 1.9 times 100%. So in this case, you will be able to get about 10.5%. So let's just call it 10% or 11%. Let's just call it 11%. Okay, 11% in physics is, of course, not the best, but is acceptable, I would say. So if you go up to like more than 15%, then it's not very good. Okay, so in this case, then you can say it's really up to you whether you say it's significant or not, because it's kind of relative for this approach. The last approach that people would use, but I don't think is really necessary, is to use something called the R value. In mathematics, you can find out the R value of a set of data and the line of best fit of a linear line. So that is basically finding out how far it is from the straight line. So let's say you got a few data points. Alright, so the way that R value works is trying to find out the vertical distance and somehow calculate a value that represents whether or not the line is presentable of all these data. So there should be a way you can substitute all the numbers and you can just find out. You can try to study it on your own, but then I don't think it is being much appreciated in IA in physics, so I don't quite recommend to the students. So I would say, but just by doing number 1 and at most 2, actually number 1 should be pretty much okay. Then it will be enough for judging the random error. Lastly, systematic error. This is much more straightforward. So in our framework, as we said, this is the equation that we have. Okay, and once again, if you look at this equation, then it tells us that there's no y-intercept, supposedly, because s is supposed to be proportional to root h. So in theory, the line should pass through, and also the max mean line should cover the origin. So one way of doing it is you could just simply observe from the graph that to see whether or not, I mean, this is literally the origin, right? And the max mean line is covering the area here only, right? Here only. And so obviously it doesn't cover the origin at all. You could also tell by looking at the range of the y-intercept, which is the one that we calculated here. You can see the range doesn't cover 0, right? Or just by looking at here also, right? So you can judge easily. And because of that, then the answer would be yes. Okay, and of course you have to explain why. And the reason is you can say, like, supposedly s should be proportional to root h, and that means the range of the max mean line should cover. Of course, I'm trying to put down the brief wording. You can phrase it in a more detailed and precise wording. Should cover the origin. All right, but then, however, it isn't, or it doesn't. It isn't covered by the max mean line. Okay, so there must be significant systematic errors, which for this student, he would need to discuss it in the evaluation section to maybe think of any possible errors, source of errors that he could locate and discuss why there is a systematic error. If you go forward to the next page, there is one more very short question that I would like to ask you, and that is the difference between linear relationship and proportional relationship. Okay, and I will want to address here because that somewhat is related to what we just discussed. So let me give you 10 seconds to think about it. What's the difference between these two? The answer can be explained very easily by mathematics. So for linear equation is y equal to mx plus c, while proportional relationship, when we talk about proportional, usually is referring to directly proportional. Although I know there is something called inversely proportional, etc. But usually when you talk about that, it's referring to directly proportional. So that will be y equal to kx. There's nothing attached at the back. So that's why when you are talking about proportional, then it should pass through the origin. While when you're talking about linear, it could be a line like this, right? As long as it's a straight line. Or it could be something like this also. Alright, as long as it is a straight line. Or I think it could also be a line that is like this, right? If you have a negative slope. Of course, you still could call the line which pass through origin as a linear, because this is when c equal to 0. Okay, so linear is more like a higher order, while proportional is like a subset of linear relationship. The reason why I talk about this is because when you try to judge your systematic error just now, you have to understand that it was because our original framework told us that it is supposed to be proportional, and that means passing through the origin. Then we check whether or not the mass mean line cover the origin. In the case, maybe you have your own IA with other physical framework, that means the equation, then you may have a y-intercept after you, even if you linearize it. So in this case, what I would suggest you to do instead is not checking the origin, but then checking whether or not the mass mean line, so maybe you still have a mass mean line like this maybe, alright, it doesn't pass through origin, but that's totally fine. It's more about check whether or not, maybe I'll draw better, right, check whether or not it passed through the point C. So for example, if C is somewhat here, then you are happy because that is the area that it covers. Okay, and if it is not, then certainly then you can declare there is a significant systematic error. Let's make a summary. In this video, you learn about how to produce the process data table from the raw data table. You also learn how to apply the idea of linearization with the real data from the experiment. You also learn how to find out the range of the slope from the mass mean line, as well as the range of the y-intercept. Lastly, you also learn how to determine whether or not there are significant random error and systematic errors. I hope you enjoy learning with me. If you do so, hit the like button now and subscribe to my channel if you want more content. I will see you again in the next video. Bye.